Okay, welcome ladies and gentlemen. Today we are going to talk a little bit about LeChatelier's principle. And Chatelier's principle says if a change is made to a system in equilibrium, the system will shift to account for that change. And we're going to spend the rest of this little video here discussing exactly what it is that means. But let's first kind of look at a little example here. So if you remember in another video when we were looking at this last time, we were talking about this little equilibrium that was established in a high school, where we had initially 300 single girls, 300 single boys, and 0 couples. People start meeting each other, people start breaking up, till we reach this equilibrium point where the number of single girls, single boys, and couples is staying about the same. Now, again, it's not the same single girls, single boys, and couples, but about the time that one couple forms, another one breaks up, and these numbers stay constant. Now, once we get to that balance, once we get to that equilibrium, we could do something that Le Chatelier would call a stress. We could change it, we could add to it, we could mess with it. So something that would mess with this thing a little bit is adding more boys. What if somehow or other, 20 new single boys came into this high school? What would happen to our equilibrium? Well, what Le Chatelier would say is it would cause a shift to occur. We've added some more single boys. We've increased the number of these. So maybe these young ladies here start to see something new, start to see something they like. So you would say it would cause a shift to the right. In other words, there would be more couples that would form after those single boys are added. And so adding something, notice, to this side of the equation, the side with the boy and the girl, is going to cause us to shift to the opposite side. Now, it's something really similar that could happen if we add more girls. Again, we have a few young ladies. These young men see something that they might like. That's going to cause a shift to the right as well. So we added something to the left side of our equation. It causes our equation to shift to the right, meaning more couples form. Now let's imagine we somehow, who knows how this would happen, we add more couples. So somehow, instead of 100 couples, now there's another 20 couples in here, let's say. What would happen in that case? I think this is a little bit like what happens when couples go off to college together when that happens. Sometimes they see a great world out there of single people and they decide, well, they'd rather be single. And if this analogy works how chemical reactions do, if we add couples, we're going to shift to the opposite side, we're going to shift to the left, we're going to shift in this direction. So adding couples would cause there to eventually shift in the direction of a greater number of single people. So hopefully that makes some kind of sense to you. And what we're going to do is sort of, as we go here, get a little more detailed with this and apply this more to actual chemical systems. So just as a reminder, just to completely clarify what we mean by shifting, adding more of a certain substance, now this is to a system that's already at equilibrium, if we add something to that system, it's going to shift away from that side. If we remove something, it's actually going to shift it towards that side. And we're going to look at some examples here. Actually, let me just... if, and these double arrows are supposed to be up here. Let's move them back where they should belong. So if we have a system that's at equilibrium, and we take that system and we add SO2, what that's going to cause to happen, what the Chatelier's principle tells us, is the system is going to shift to the right. So adding SO2 to the system, SO2 is on the left, it's going to cause a reaction to shift to the right. So it says, how would the reaction below be affected by adding SO2? We could say that it's going to shift right. Removing oxygen. So again, we have this system here, this thing, it's in balance, it's at equilibrium. If we do something like remove oxygen, if we take it away, the system is saying, oh my gosh, I'm out of balance, I need to make more oxygen. So what the system is going to do is it's going to shift to the side that has oxygen in it. It's going to shift left. Shift L for left. So as we see, like it said on the last side, if we add something, it shifts to the opposite side. If we add SO2, there's too much of it. The system has to get rid of it and make SO3. If we do the opposite, if we remove oxygen, the system doesn't have enough of it to restore that little balance, to restore that equilibrium. It needs to make oxygen, so it's going to shift it to that side. It's going to shift to the oxygen side. Adding SO3, well, when we're adding SO3 to a system that's in equilibrium, we're adding something to this side. It's going to shift to the opposite side. So we've added something to the left, which means the system will shift it's supposed to be. So we're adding something to this side, so it's going to shift to the opposite side, it's going to shift left. So add something to one side, it's going to shift to the opposite side. Remove something from one side, it's going to shift to that side. And if this part's not clear to you, I'd suggest maybe stopping it, go back and through the last minute or two here, see if you could kind of wrap your brain around what I'm saying so far. I'm going to explain a little more detail about what exactly I mean by shift on the next slide, just so you know. Now, what exactly do we mean when we say shift? When you think of this, I want you to think of like a teeter-totter, how a teeter-totter shifts. When one side goes up, the other side goes down. It's physically impossible for it to happen any other way. Or, for instance, in our little couples scenario that we were just talking about, there's my professionally drawn young lady. There's, so, single boy, single girl. If we're going to have a situation where we make more couples, it's physically impossible to have more couples without having less single people. So in this case, if we're going to shift to the couples side, by the very definition of forming a couple, there has to be less single people than there were before. And vice versa. If a couple breaks up, there has to be less couples and more single people than there were before. These chemical reactions work the same way. When I say shift to the right, what I mean is the amount of the product side is going to go up. So if we're shifting to the right, this side's going to go up, and the amount of these things are going to go down. So like a teeter-totter, here's my little teeter-totter. A teeter-totter being lifted upwards in this direction. This side of the teeter-totter goes up, the product side goes up, these things go down. If it's a left shift, it's the total opposite. So if I'm going to shift to the left, what does that mean? It means the reaction's proceeding in this direction. Okay, so that means that these two things, these are on this side of my teeter-totter, the left side of my teeter-totter is going up. And if the left side of my teeter-totter goes up, the right side has to go down. So when I say shift left, what I mean is the concentration of this is going up, the things on the left side of the arrows are going up, and the concentration on the right is going down. And they always have to be in opposites like that. There's no possible way to get more of this without having less of this. It's absolutely physically impossible. So again, a left shift means these things on the left, their concentration increases, and these things on the right, their concentration decreases. If I said a shift to the right, it would be the total opposite. If I'm going to shift to the right, this stuff right here, the amount of that has to go up, and the amount of stuff on the left has to go down. That's what we mean when we say a right shift. Okay, so hopefully you're with me so far. Again, if you're a little unclear about what we mean by shifting, maybe stop, back up, look at the last couple of minutes, and see if that makes some sense to you. So what we're going to talk about here is, so far we've been talking about concentration and how that affects LeChatelier's principle. We're going to talk about a couple other things. We're going to talk about pressure. So let's say we have this reaction of gases and it's at equilibrium. We could change the pressure of the system. For example, suppose we had this reaction going on in a little syringe. Okay, what I could do is I could decrease the size of the syringe, so the syringe is one side, and I could, let's just say the reaction's going on inside this syringe, I can make the syringe a little smaller, which would be a way to increase the pressure, because I've squeezed the syringe down tighter, there's more pressure in the system. So what is that going to do? Well, in reaction with gases, if we increase the pressure, it's going to shift to the side that has less overall moles of gas. So let's examine this a little bit. We've got a coefficient of 2. That means in our balanced chemical equation there's 2 total moles of gas on this side, whereas here there's only 1 total mole of gas on that side. So it says, what is the effect of increasing pressure? And we look at our rule. In reactions with gases, adding pressure shifts the reaction to the direction that has less overall moles of gas. This has 2 moles, this has 1 mole. 1 is a smaller number than 2. So increasing pressure, that's going to shift us to the right. That's the side with less moles of gas, meaning the amount of N2O4 is going to go up and the amount of NO2 is going to go down. So we're going to shift to the right, we're going to have more N2O4, and we're going to have less NO2 when that happens. Now if we, reducing pressure is going to do the exact opposite thing, as you might expect. It's going to shift to the side with more moles of gas. So if we expanded the size of our syringe, or we somehow reduce the pressure in the reaction vessel, that's going to shift us to the left, meaning more NO2 and less N2O4. So that's gases. Now, pressure only affects gases, not liquids, not solids, not aqueous solutions. This is only related to gases, so make sure that you're aware of that. So another thing that can affect equilibrium is the temperature. So when we're talking about this, it's really important to think about whether the reaction in question is endothermic or exothermic, because it's going to make kind of all the difference as far as what change in the temperature will do. So this particular reaction, the one we were just looking at, is an exothermic reaction. How I can tell that is it's showing me this reaction plus heat. So this reaction is giving off heat energy. So when this equation was written and that plus heat was added here, that was a way to communicate that this reaction is exothermic. Another way of communicating that is we could just be told that delta H is a negative number. If you recall from our energetics unit, negative delta H is our exothermic. So once we wrap our brain around that little fact, this works just the same as before. We're going to think of heat energy as a product. So it says, what is the effect of adding heat energy? Okay, well, it's an exothermic reaction, so we're going to think of heat energy as a product. Notice that heat is written on the right. So if we add heat energy, in other words, if we increase the temperature, heat energy is here on the right side, so that's going to shift us left, meaning the amount of this goes up, the amount of this goes down compared to what it was before. Again, this all starts with assuming you get a system that's at equilibrium, and then we add heat energy to that, we get a shift to the left. If we remove heat energy, as you might expect, it's going to be just the opposite. So we're thinking of heat as a product here. So it's it's as if we're taking something away from this side when we lower the heat energy of the system. And so we're taking something away from the right side. So when we take something away from one side, it shifts us to that side. So we're going to shift to the right, meaning we're going to get more of this, and we're going to get less of this. So that in particular can be one of the most confusing parts of this, but we're going to look at some more examples. But it's definitely worth mentioning at this point that if this reaction were endothermic, we would be thinking of this a little differently. If this reaction were endothermic reactions require heat energy. The endothermic reactions would have heat over here on this side. So our heat would be over here if this was endothermic. And the answers to both of these bullets would have been opposite. So it's really important to recognize whether a reaction is endothermic or exothermic if you're answering questions like these. Okay, so another couple of points here. Catalysts don't change equilibrium values. They just help you get to equilibrium faster. So catalysts help you get to equilibrium faster, but they don't change equilibrium values. And the only thing that causes that KEQ value to change is temperature. So, and I'm going to talk more about what the rest of this bullet is saying here in a second when we look at an example. Okay, so let's look at one of these little tables. Let's just say we have this kind of generic reaction. So here we have some changes. So we've got this system and its equilibrium. We have some changes, and we're to say what direction will it shift, and what will happen to all these things. What will happen to the concentration of A, what will happen to the concentration of B, and what will happen to the concentration of AB. So the first change is addition of A. So we've got a system at equilibrium. Notice we're adding something to the left side. So since we're adding something to the left side, when we add something, it shifts to the opposite side. So that's going to cause a shift to the right. So then what's going to happen to the concentration of these things? So remember, it works like a teeter-totter, okay? If we are shifting to the right, it means the concentration of this is going to go up over here, and the concentration of this is going to go down. So the concentration of A is going to go down, concentration of B is going to go down, concentration of AB is going to go up. Now you might say, what are you talking about here? This change says addition of A, so how can the concentration of A be going down? What we're talking about on these kind of tables is right after I add the A, what's going to happen. Yes, I'm adding the A, so the concentration of A is going to go up a little bit because I added some, but what's also going to happen is the system's going to be out of balance and out of equilibrium, so it's going to get rid of that A by shifting to the right. So in the process of undergoing this shift, these two things are going to go down and this is going to go up. The value of K, there's only one thing that changes K, or KEQ, or KC, whatever you want to call it, and it's temperature. So that's not going to change the addition of A. Now if we remove B, erase this part up here, if we remove B, so remember our rule is you add something, you shift to the opposite side, you remove something, you shift to that side. If we remove B, the system is lacking in B, so we're going to shift to the side that we remove the B from. So we're going to shift there. And again, it's like a teeter-totter. We're shifting to that side. So our teeter-totter is tilting up in this direction, if you will, by shifting to the left, meaning the amount of A and B are going to go up. And it is physically impossible for the amount of A and B to go up without the amount of AB to go down. It's absolutely impossible for it to happen any other way. And the value of K then is not going to change, because the only thing that changes that is temperature. when we increase pressure, the higher the pressure, it's going to tend to shift to the side with less moles of gas. So if you notice on this side, we have a mole of A and a mole of B. That's a total of 2 moles. So there's 2 moles here. AB, there's only 1 mole on this side. We have 1 mole of AB. Essentially, we're just summing the coefficients. That's a coefficient of 1, that's a coefficient of 1, that's 2, and only 1 mole over there. Increased pressure shifts to the side with less moles of gas. That's a shift to the right. So our teeter-totter is tilting up like this. So this is the one side of the teeter-totter. That's going to go down. And the moles of AB is going to go up. So A and B both go down. AB goes up. No change there. The only thing that changes that is temperature. And lastly, addition of AB. When we add something to one side, it shifts us to the opposite side. So that's going to shift us to the left, meaning the amounts of both of these go up, and the amount of AB is going to go down. Again, only thing that changes this is temperature. So that's our first example. Again, if you're a little lost, maybe go back, take another look at it, go back through it, see if you can wrap your brain around it. I'm going to go on and do one more example here. Okay, so it says, consider the exothermic reaction at equilibrium. Consider the effects of the changes below. So one thing I'm going to do is I'm going to say, aha, it's telling me exothermic. So to help myself, I'm going to write a plus heat here, because I know that exothermic reactions give off heat energy. So it's convenient to think of heat energy as a product. So if we increase the temperature, we need to think about the shift. Once we wrap our brain around the fact that this reaction is exothermic and therefore heat is going to be thought of as a product, this temperature shouldn't throw us off too much. The hard part is making that little connection there. If we increase temperature, notice I've got temperature over here as a product, so increasing temperature is as if, this is just kind of a way of thinking about it, it's as if I'm adding something to my right side, my product side, which causes me to shift in that direction, and we shift in that direction, meaning A goes up, B goes up, and AB goes down. Now, value of K. Temperature does affect value of K. So let's think about this a little bit. Let's think about this mathematically. If we write our equilibrium expression, it's going to look like this. KEQ equals K, KEQ, KC, same thing, remember. It's going to be products on top over reactants on bottom. So what's really happening is as we change the temperature, the value of K changes, and everything kind of adjusts in response to that. But let's kind of think about it this way. So my system has undergone a change here, which has caused a shift to the left. It's caused A and B to get larger, and it's caused AB to get smaller. So whatever our KEQ was before, well, now this number is smaller than it was before, and this number is bigger. So we went from this number getting a little bit smaller, this number getting a little bit bigger. If you kind of think about how the math works, that's going to make the value of KEQ get smaller. So understand this is just a way of thinking about it. The way I'm speaking about it, the cause and effect is kind of a little bit backwards, but it's a good way to just think about it. If you think about your equilibrium expression, any temperature change that you make that causes the amount of product to go down is also going to cause the value of K to go down. And if you understand KEQ, remember, the smaller the number is, the less product you have at equilibrium. So we've made a temperature change that causes the amount of product to go down, so that's going to cause K to go down. If we decrease temperature, hopefully it's clear that everything is going to be exactly the opposite. It's as if I'm taking something away from that side. So when we take something away from one side, it shifts us to that side, meaning these have to go down. The amount of this is going to go up, and the value of K is going to go up. Increase container volume. Okay, so this is a little tricky, but we have to think about what is this really going to do. So let's say this reaction is going on in a syringe, and it has a certain volume, and then we expand that syringe. What this is trying to get at is what's going to happen to the pressure in here. Hopefully you recall volume and pressure are inversely related, so we've made the container bigger, meaning pressure is going to go down. So if pressure goes down, remember pressure affects moles of gas. If we increase the pressure, it shifts to the side with less moles of gas. If we decrease the pressure, it's going to shift to the side with more moles of gas. So in this case, we're increasing the container volume. What's important to note here is that pressure is going to be decreasing when we do that, since those things are inversely related. So that's going to shift us to the side with more moles of gas. This side has 2 moles. This side has 1 mole. So A goes up, B goes up, AB goes down, and value of K is unchanged. The only thing that can change that is temperature. Okay, so suppose we have a system that had a catalyst. We saw in a previous slide, the only thing catalysts do is help you get to equilibrium faster, but when you get there, everything will be the same as what it would have been without the catalyst. So the catalyst is going to be no change across the board. So that's it for LeChatelier's principle. It definitely can be a little bit confusing. Don't be afraid to go back and take a look. Maybe look at it again, see if you can make some sense out of what's going on here. What we'll do is we'll be able to address some of your questions in class if you have them. And what we're going to be working on is this page in your workbook. You may want to pause that and find it. But we could just take a quick look at this. You do not need to complete this at this point. We can work on this in class. But just to give just another quick example here, if we're still kind of wondering about this stuff, I'm going to leave that for now, but just to maybe look at 1 or 2 examples here from question 2, just so we can see something a little bit different. So it says this reaction is at equilibrium, the stress is below. Reply to the equilibrium mixture. In what direction, if any, will the reaction shift? Actually, why don't we do this? Pause it, either look at the question on the screen and answer it that way, or find it in your workbook. Let's just pause it, take a few seconds, see if you can figure out the answers to number 2, and then unpause it, and we'll talk about it. Okay, so did you really pause it? Hopefully you did. More CO2 is added to the system. So if we have the system at equilibrium, we add more CO2. It wants to know what direction it should shift. We added something to the left. It's going to cause a shift to the right. Hydrogen is removed from the system. The hydrogen's over here. We're taking something away from the left side. It will shift us to the left side. So B is going to cause a left shift. Carbon monoxide. Carbon monoxide is that. And carbon monoxide is added to the system, so we're adding something to the right. That would cause a left shift. A catalyst is added to the system. That's going to cause no change. It's just going to get us to equilibrium faster. And pressure is increased. Okay, well, pressure is going to shift to the side with less moles of gas. This is a little bit tricky. Notice here we have CO2 and H2O. That's 1 mole plus 1 mole. There's 2 total moles on this side. On the right, 1 mole plus 1 mole, 2 total moles here on this side. So the number of moles is actually the same. So actually in this instance, pressure is going to have no effect. Okay, so that's it for now. Thanks for listening, and we'll see you soon. Have a good day.